In this lecture, we're going to be looking at the centre of mass. So this lecture is based on sections 9.1 and 9.2 of your textbook. First of all, a quick recap of the most important ideas in the last lecture. In the last lecture, we were looking at mechanical energy, and we said that it was conserved when non-conservative forces do no work. So the change in mechanical energy, which is equal to the change in the kinetic energy plus the change in the potential energy, is equal to 0. Now, potential energy is stored energy, so it can be calculated as the negative work done, which is negative the integral from the initial position to the final position of the force times dx. So we said the total energy, E, of a system can change only by amounts of energy that's transferred to or from the system. So if we do work on the system, then we're adding energy to it, and that leads to a change in energy, which is equal to the change in the mechanical energy plus the change in the thermal energy, which is generally work done against friction, plus the change in the internal energy, which we'll learn more about in the thermal topic. So far we've been talking a lot about particles or particle-like objects, but as you may have noticed, most everyday objects aren't particles. So this is why it's really useful to learn about the center of mass of a system. So the center of mass of a system is the point that moves as though all of the system's mass were concentrated there and all external forces were applied there. So let's find the center of mass for an unbalanced stick. For this stick, you can see the center of mass is just at the end of the yellow point there. So hopefully you can see that clearly. Now, if I were to throw the stick so that it undergoes projectile motion, it will rotate, but the center of mass should move as a nice projectile. So let's have a look at that. With this stick, it has been weighted, so one end is heavy and the rest is all made of wood. Okay, let's look at it as it's thrown. So hopefully in this clip you saw that the center of mass of the stick traced out a parabolic path, just like we've seen projectiles do. So we could model all the mass of this stick as concentrated at that center of mass, and then that center of mass behaves just like a normal projectile, even though there's lots of rotations and other things going on the rest of the stick. Okay, so this is just a comic that I find slightly amusing, so I'll just give you a chance to read this. Okay, so we've seen why the center of mass is so useful, but how do we find it? Well, it's physics, so there's an equation for that. So we can find the x-coordinate of the center of mass using this equation. So we've got 1 over the total mass, and then we need to sum up each of the particles making up our object. So it's the mass of each particle times the position of each particle, and if we sum all those and divide by the total mass, we'll end up with the location of the center of mass. So let's have a go at this sample problem. Okay, so in this problem we've got 3 particles. We've got x1, well, this is distance x1, and it's got mass m1, which is equal to 1 gram, and this is 1 centimeter. Now we've got m2 at x2, which is 2 grams at 2 centimeters, and then we've got 3 grams at 3 centimeters. And so the x-coordinate of the center of mass is equal to the sum of m1 x1 plus m2 x2 plus m3 x3 over the total mass, which is m1 plus m2 plus m3. So we can substitute in. We've got 1 gram times 1 centimeter plus 2 grams times 2 centimeters plus 3 grams times 3 centimeters divided by 1 plus 2 plus 3 grams. So this is grams and this is grams centimeters. And so we've got 1 plus 4 plus 9, which is 14, divided by 1 plus 2 plus 3, which is 6. So this is equal to 2.3 centimeters. So we found the x coordinate of the center of mass of this system. So you can see it's going to be around about here, which is kind of what we expect because this one here is heavier than these ones. So you'd expect it to be closer to the third mass than the first two. So in this example problem, we're told that 70 Ophiuchi is a binary star system located 16.6 light years away from the Earth. It is in the constellation of Ophiuchius. The two stars orbit each other at an average distance of 23.2 AUs, where AU stands for astronomical unit, and 1 AU is the average distance between the Earth and the Sun, which is equal to 3.844 times 10 to the 8 meters. The heavier star, 70 Ophius A, has a mass of 0.90 solar masses, while the lighter star has a mass of 0.7 solar masses. 1 solar mass is the mass of the Sun, which is 1.989 times 10 to the 30 kilograms. When the stars are at this average distance, how far is the center of mass of the system from the center of 70 Ophius A? So to solve this problem, let's start by drawing a diagram. So here we've got our first star, which is 70 Oph A, and its center of mass will represent by this dot, and we'll say that that is located, we'll call it XA, is equal to 0, because in this problem we're trying to find out the distance of the center of mass of the system from this point. So this is our origin point, so this should be located at 0. And then we've got a second star over here, which is 70 Oph B, and it's got a center of mass here, and that's located at XB. And we're told in the question that this average distance between these two, which is what this is located at now, is equal to 23.2 AU. So because that's 23.2 AU from the origin, it is at x is equal to 23.2 AU. And we're told that the mass of star A is equal to 0.90 solar masses. So solar masses we can draw with this little symbol here. And mass B is equal to 0.70 solar masses. Now we are given the information in the question, so we could convert from AU and from solar masses into meters or kilometers and into kilograms, but it's not needed in this case. So we're going to save ourselves some time by not doing that. So our equation for the center of mass is equal to the sum of xi mi over the sum of mi, and we've just got two masses, 2 points in this case. So we've got XAMA plus XBMB over MA plus MB. But we said here that XA is equal to 0. So this term here, this whole thing is equal to 0. So we can write that as XBMB over MA plus MB. So now I'm going to show you why we don't need to convert the units. If you do convert the units, you won't get it wrong. It'll just take a little bit longer. Okay, so I'm going to put the units after this in square brackets. So XB is given as a distance in AU, and MB, that's given in solar masses. And then MA plus MB, both of those are solar masses. So the units for this is solar masses. So these solar mass units cancel out, and then my final answer will be in atomic units. So let's now substitute in. I've got 23.2, sorry, not atomic units, astronomical units. So 23.2 times 0.70 over 0.90 plus 0.70, and solving that on the calculator, I get 10.15 AU. So we can write this as 10.2 AU. And so along this line, it is slightly closer to star A than star B, which is what we expect, as star A is the heaviest star. So if these were going in circular orbits, which it actually turns out they're going in elliptic orbits, but if they were going in circular orbits, they both move in circles about this center of mass point here. So we've seen how to find the center of mass for a one-dimensional object, but it's also possible to find the center of mass for objects which have more than one dimension, such as 3 dimensions, like most of the objects around us. So in order to do that, we just treat each of the dimensions separately and use these same equations here to calculate the x, y, and z coordinates of the center of mass of that system. So to practice using this, for Physics 1A, try homework set 3, question 2, or for Higher 1A, also question 2. But now let's have a go at this example problem. So in this example, we've got 3 particles. M1 has a mass of 1 kilogram, M2 has a mass of 2 kilograms, and M3 has a mass of 3 kilograms, and they form an equilateral triangle with side lengths of 10 centimeters. We need to find the center of mass of this triangle. Okay, so let's put M1 at our origin. So M1 has X1 is equal to 0 and Y1 is equal to 0. Now we'll put M2 10 centimeters away along the x-axis. So this here is 10 centimeters and this is M2 and it's at location x2 is equal to 10 centimeters and y2 is equal to 0. And then it's an equilateral triangle. So M3 is up here. So M3, which is 3 kilograms, this is 2 kilograms, this is 1 kilogram. It's up here. We'll be able to calculate this height and we'll have to do that soon. We know this length here is 10 centimeters. This length here is 10 centimeters because it's an equilateral triangle. And we've got 60 degrees here because all the angles in an equilateral triangle add to 60 degrees. So hopefully you can see that M3 has to be above the midpoint between M1 and M2. So that tells us that the x coordinate has to be 5 centimeters. And so we just need to calculate Y3. So to calculate Y3, we've got this length here is 5 centimeters and this length here is 10 centimeters. So we can use Pythagoras' theorem and write, well, 10 squared is equal to 5 squared plus Y3 squared. So that's just considering this triangle here with side length y3, side length 5, and side length 10. And solving this, we can say, well, y3 is going to be equal to the square root of 10 squared minus 5 squared. So this is equal to 8.66. So we can say this is equal to 8.66 centimeters. Okay, so now we need to find the center of mass. Okay, so we can find the center of mass. The x center of mass is equal to x1 m1 plus x2 m2 plus x3 m3 all over m1 plus m2 plus m3. So this is the total mass here. So we've got 0 times 1 plus 10 times 2 plus 5 times 3 over 1 plus 2 plus 3. So this is over 6. We've got 20 plus 15, 35 divided by 6. Solving that gives us 5.83. And that's centimeters, because this was centimeters times kilograms, and we're dividing by kilograms. So the y for the center of mass is equal to y1 m1 plus y2 m2 plus y3 m3 over m1 plus m2 plus m3. And this is equal to 0 times 1 plus 0 times 2 plus 8.66 times 3 divided by 1 plus 2 plus 3, which is 6. So solving this on the calculator, we get 4.33 centimeters. Okay, so if we want to give the center of mass, one way to write it is in unit vector notation. So we can say, well, the location of the center of mass is 5.8 I, where I is along the x-axis, plus 4.3 J centimeters. So let's just sketch where it is. Now this height up here is 8.66, so 3 is half that. So height-wise, we're exactly halfway up, which is what we'd expect because this is 3 kilograms and these two sum together to give 3 kilograms. And then we're a little bit to the right of center here. So we're around about there. And that is also what we'd expect for the x-coordinate. Because the second mass is heavier than the first one, we'd expect to be slightly closer to the second mass than the first one. Now we can also find the center of mass of a continuous object. To find the center of mass of a continuous object, we need to break it up into little components, each with a mass dm, and then sum across all of these contributions through integration. So I think it's easiest to see how to do this through an example. So in this example problem, we've got a rod. So let's sketch our rod here. And we're told that one end is at the origin, so this is x equals 0. And we're told that the linear density varies along its length, and it's described by this equation, and it's 1 meter long. So the other end of the rod is at 1 meters, x equals 1 meters. So if we want to work out, well, how much does a little increment here at a distance x from the origin, and it has width dx, contribute to the center of mass, then we'll need to use that x for the center of mass is equal to 1 over m times the integral of x dm. So we'll need an expression for dm in terms of x. So dm physically means, well, how much does this little component here dx weigh? So we can see that, well, dm is going to be equal to the density times dx. So we can substitute in the density from up here. So 2 plus 3x dx. So we can say, well, x for the center of mass will be 1 over the total mass times the integral. Now we do have the limits on our integral. We're going from x equals 0 up to x equals 1 of x times dm, where dm is 2 plus 3x dx. So this is equal to 1 over m times the integral from 0 to 1 of 2x plus 3x squared dx. So let's integrate that. We've got 1 over m times x squared plus x cubed from 0 to 1, which is equal to 1 over m times 1 plus 1, which is equal to 2 over the total mass. So now what we're going to have to do is find the total mass of this object. So the total mass of the object we get by just summing up each of the little incremental masses, so the dm's. So to do that, we need to integrate over all of dm. Now, we'll use this expression for dm here, so we'll be integrating along the entire length from 0 to 1 of 2 plus 3x dx, and when we do this, we end up with 2x plus 3x squared on 2, which is equal to, and we're evaluating it at 0 and 1, so this is equal to 2 plus 3 on 2, which is equal to 3.5 kilograms is the total mass of this rod here. So this tells us that the x for the center of mass is equal to 2 divided by 3.5, which is equal to 0.57 meters. Okay, so let's just logically check that. That is around about here. Now, it's getting more dense as we get further along to this end. As at this end, we've got a density of 2 plus 3, which is 5, whereas down this end, we've got a density of just 2. So we would expect the center of mass to be closer to the right end than the left end. Now, we can also work out the center of mass of composite shapes. So let's consider this composite shape here, where we've got a rectangle with width W and length L and a circle with a radius R, which are joined together, and they've got a constant surface density. So let's let that constant surface density be sigma. And in this question, we're asked how far below the top of the rectangle is the center of mass of the system. So the best way to consider this is as two shapes, and then we can use, well, the center of mass is going to be equal 1 over the mass of shape 1, so we can have mass 1 times x1 plus mass 2 x2. So if we can find these for each of the shapes, then we can find it out for the total thing. So hopefully you can see by symmetry that there's a line of symmetry and sigma's constant. So the center of mass is going to be along this axis here. So what we're going to need to worry about finding is, well, how far down from this line is it? So the center of mass of the rectangle, that's going to be right in the middle of the rectangle here. So it's going to be a height L on 2 away from the top of the rectangle. And the center of mass of the circle, well, that's going to be right in the middle of the circle. So from this line up here, there's going to be a distance L plus R. So this will be L plus R. Okay, so it's only asked us to find how far below the top of the rectangle is the center of mass. So let's call this dimension down here the X dimension, and we're trying to find the X center of mass. Okay, well, to do that, we're going to need to know the mass of each of these shapes. So for the rectangle, the mass of the rectangle is going to be equal to the area of the rectangle, which is W times L times the surface density. And the mass of the circle is going to be equal to the area of the circle, which is pi r squared times the surface density. So we've now got the location of the center of mass of each of these shapes individually, and we've also got the mass of them. So we can put that into this equation. So the center of mass is at M1, which is WL sigma, times X1, which we said it was at L on 2. And then M2, that's pi r squared sigma, and then times X2, which we said was L plus R, divided by the total mass. So the total mass is the mass of the rectangle plus the mass of the circle. So that's sigma times WL plus pi r squared. So you can see that sigma occurs in every term and so is cancelling out. So we can write this as WL squared on 2 plus pi r squared times L plus R times WL plus pi r squared. So we've now come up with an expression for the center of mass. Okay, now we've seen Newton's second law so many times, but the lovely thing about Newton's second law is that we can also apply it to systems. So by that we mean that the net force is equal to the total mass of the system times the acceleration of the center of mass of the system. So you can see this is going to make the center of mass really powerful. And so the acceleration of the center of mass of the system is equal to 1 over the total mass of the system times the sum of all the masses of the little components times their acceleration. So to think about how we can use this, imagine two people standing on skateboards holding a long pole. The person on the right pulls themselves along the pole towards the right, and the system consists of the two people on the skateboards and the pole. So which of the following statements is true? There are no external net forces acting on the system, or the external forces are to the right due to the person pulling themselves along the pole, or the external forces are to the left, they oppose the motion of the person along the pole. Okay, so the correct answer to this one is actually this first one. The person pulling themselves along the pole is an internal force because they are part of the system. So anything they apply to the other members of the system is an internal force. So if somebody pulls themselves along the pole, then they will move, but the net external force is 0. So the acceleration of the center of mass of the system should also be 0. Okay, so we said that when no external forces act, then the acceleration of the center of mass must be 0, which means the velocity must remain constant, the velocity of the center of mass. So we can calculate the velocity of the center of mass using this expression here. So the velocity of the center of mass in the x direction is equal to the derivative of the x location of the center of mass with respect to time. So you can see that we can do that as 1 divided by the total mass, because that's independent of time, times the sum of the little masses, and then we've got dxi dt, and dxi dt is just the velocity of each of those particles I in the x direction. So this same equation holds in all the dimensions. So we could come up with the same one for y, with a y here and the y here, and z with a z here and a z here. So that tells us that we've got a vector equation where the vector center of mass is equal to 1 over m times the sum of each of the particles' mass times their individual velocity. So we did a few demos at this point to check that this actually worked. We considered the center of mass of the skateboard systems with the pole. We also considered a couple of collision carts and what happens when there's an internal force pushing them apart. So to practice using this, if you're in Higher Physics 1A, have a go at homework set 3, question 3. So let's have a look at an example now. Okay, so in this problem, we have a car with a mass of 1.25 tons traveling at 30 kilometers per hour. Okay, so let's draw it here. So it's got a mass of this car is equal to 1.25 tons, and its speed is equal to 30 kilometers per hour. And it's going this way. Now it's ran from behind by a second car with a mass of 2 tons. So here's the mass 2, which is 2 tons. And this one here is traveling with a speed of 60 kilometers per hour. So let's call that U2. We'll call this one U1 and this one U2. The two cars stick together. And so we're asked, what is the speed of the center of mass before the collision? So we know that the speed of the center of mass is equal to 1 over the total mass times m1 v1 plus m2 v2. And so we can say this is 1 over 2 plus 1.25. That's 1 over the total mass times m1, which is 1.25, times 30 plus 2 times 60. So this is equal to 48.46 kilometers per hour, which is equal to 48 kilometers per hour. And then in part 2, we're asked what is the speed of the cars after the collision. So since there are no external forces here, all the forces come from the second car, which is part of this system, we know that there is no acceleration of the center of mass. So the V center of mass remains at 48 kilometers per hour. And that is still equal to the total mass, which is 2 plus 1.25 times m1 times the final velocity plus m2 times the final velocity. And now they've got the same final velocity because we're told that they stick together. So we can write this as 48 point, I'll keep all my significant figures. So 48.46 times, adding these together, I've got 3.25 is equal to the final velocity, which is what I'm trying to find, times m1 plus m2. But m1 plus m2, that's just the total mass. That's what this 3.25 is. So this cancels out, and that tells me that the final speed is just the speed of the center of mass, which is the 48 kilometers per hour. Okay, so this is quite a fun problem. So we've got a disc with another kind of disc cut out of it. So the question asks us, where is the center of mass of the illustrated plate? The plate has uniform surface density. So let's let the surface density be sigma. So we can actually model this system as a big plate with a surface density sigma, and then this smaller plate on top of it with the surface density minus sigma, because this one here is then subtracting away from this surface density. So to find the center of mass, let's draw on some axes. Let's draw x-axis this way and y-axis this way. Now hopefully you can see with the y-axis it's absolutely symmetric. So we'd expect the center of mass in the y direction to be along this x-axis here, the y equals 0 line. So we're just going to need to worry about, well, where is the center of mass along this x-axis here? So let's start by working out the center of mass of this big disk with radius 2r. So x center of mass for the 2r disk is just going to be right in the middle of the disk. If we didn't have this little disk cut out here, it would just be right in the middle. So we'll call that 0 at the origin here. And we can work out the mass of this big disk. So the mass of the disk with radius 2r is given by the surface density times the area, which is equal to sigma times 2r squared times pi. So that's equal to sigma times 4 pi r squared. Now we need to do the same thing for this little disk with this negative surface density. So the x for the center of mass of the one with radius r, well, that center of mass is going to be in the middle of this disk, which is here. So that's a distance r from 0. So that's actually minus r is its location. So we'll call this one here minus r. And now we need to know the mass of this disk. And that's going to be minus sigma times its surface area, which is pi r squared. So this is equal to just minus sigma pi r squared, which is what I had there already. Okay, so now I've got two shapes, and I'm combining these two shapes to find the center of mass of that combined system. So x for the center of mass is equal to x center of mass 2r, that's this big shape, times the mass of 2r, plus x center of mass for r, this smaller circle, times the mass of r, divided by mass of 2r plus mass of r. So let's substitute in. I've got 0 times sigma 4 pi r squared plus minus r times minus sigma pi r squared divided by sigma 4 pi r squared minus sigma pi r squared. So this is just 0. So on the top I've got minus sigma pi r cubed. Oh, sorry, it's positive because we've got negative times negative. Then on the bottom, I can pull sigma out as a common factor, and I've also got pi r squared, which is a common factor. So here I've got 4 minus 1. So this cancels this cancels this, and I'm left with just 1r on the top, cancelling that r squared on the bottom. So I end up with r over 3. So that tells me that my center of mass is going to be at r over 3, which is around about here. So let's just make sure that that makes sense. We would expect the center of mass to be on this side, as this side has less mass because it's got this little disc cut out. So we can write that the center of mass of the illustrated plate is r over 3i plus 0j. So in this problem, we've got an asteroid which is initially at rest with a mass of 700 tons. It explodes into 3 pieces. Okay, so here it is initially. Let's say its center of mass is here. And after the explosion, we have a 100-ton piece moving with a velocity, with this velocity. So here's m1 equals 100 tons, and it's moving this way with 2i meters per second. And then a 300-ton piece is traveling this way. So we say m2 is equal to 300 tons, and this velocity v2 is equal to 0.50I minus 0.05I plus 1.0 j meters per second. And we're asked what's the velocity of the third piece, so we need to find v3. Okay, and we can see initially it was at rest, so VCOM initially is equal to 0. And this is an internal force, so it explodes from something internal, so the VCOM final remains at 0, so it's always 0. So I can say, well, VCOM is equal to 1 over m, where m is the total mass, which is the 700 tons, which is equal to m1 v1 plus m2 v2 plus m3 v3, and these are all vectors. So we can start by working out what m3 is, because we know that m is equal to m1 plus m2 plus m3. So m3 is equal to m minus m1 minus m2, which is equal to 700 tons minus 100 tons minus 300 tons, which is equal to 300 tons. So I can say that 0 is equal to m1, which is 100 times v1, which is 2I, plus m2, which is 300 times v2, which is minus 0.50I, plus 1j, plus m3, which is 300 tons times v3. And this is divided by 700 is equal to the 0. But I can multiply both sides by 700 to get rid of that, and it still doesn't change 0. 0 times 700 is still 0. I can now divide by 100 to try and make it a bit simpler. So now I've got 2I plus 3 times 0.5, so that's minus 1.5I plus 3j plus 3v3 is equal to 0. So looking in the I direction, my I components must all sum to 0. So I've got 2 minus 1.5 plus 3 times v3 in the I direction. So let's call that v3x. And that's equal to 0. So I can see 3 times v3x is equal to minus 0.5. So v3x is equal to 0.5 divided by 3, which is minus 0.17 I meters per second. So that's in the x direction. So I've put my little I unit vector back there. Now I can look at in the j direction, and in the j direction, I've got this vector and this vector. So those things need to give me 0. So I've got 0 is equal to 3 plus 3 times v3 in the y direction. So this tells me that v3y is equal to minus 3 over 3, which is equal to minus 1 meter per second. So I can say, well, the velocity of my third chunk of asteroid is going to be equal to minus 0.17 I minus 1.0 j meters per second. So I can just check that that makes sense. If I draw it onto this diagram, it's heading back in this direction and down here. So it's heading kind of down like that. And that would be what I'd expect. I'd expect these j components to cancel out, and this one's got a faster speed in that way, but this one here is heavier with its slower speed. So I wouldn't expect too much in my I direction, which is indeed what I end up with. I end up with a small velocity in the I direction. So this is a challenging problem. A uniform soft drink can of mass 0.140 kilograms is 12.0 centimeters tall and filled to the top with 0.354 kilograms of soft drink. Then small holes are drilled in the top and the bottom with negligible loss of metal to drain the drink. So we need a hole in the top to let the air in so that it can drain out smoothly. What is the height h of the center of mass of the can and the contents? Part 1 initially, and then after the can loses all the soda. And then what happens to h as the soda drains out? And finally, if x is the height of the remaining soda at a given instant, find x when the center of mass reaches its lowest point. So we've got a uniform soda can, so let's sketch it like this. And it's got a height, capital H, and that height is equal to 12 centimeters. And the mass of the can is 0.140 kilograms, and initially it's filled to the top with soda. So the mass of the soda in the can is given by 0.354 kilograms. And then we drill a small hole in the top and the bottom, and the soda starts to drain out. And in the first part, we're asked, well, what's the center of mass of the can when it's full of soda? Okay, now the nice thing with this problem is that it's very symmetrical. So with our can, we can assume it's got the same mass up the top as down the bottom. And so the center of mass of the can is going to be equal to half the height of the can, so h over 2. And the center of mass of the soda will also be right in the middle, because initially it's filled all the way to the top, so we've got as much mass above the midpoint as below it. So the center of mass of the soda will be, well, the height of the soda divided by 2, but initially this will just be h over 2. And so the center of mass of everything is going to be equal to h over 2. So this is the center of mass of the can times the mass of the can plus the center of mass of the soda, which will be x over 2 times the mass of the soda over the total mass, which is the mass of the can plus the mass of the soda. And so since the initial height of the soda, x, is h, we can write this as h over 2 outside of the mass of the can plus the mass of the soda over the mass of the can plus the mass of the soda. We've got common factors on the top and the bottom, so it's just h over 2. And since we're told that the height of the can is 12 centimeters, this is just going to be 6 centimeters. Okay, part B then asks us what's the center of mass once it's lost all the soda. So in that case, we've got that the ms is equal to 0. So we can use this same equation here, but now we've got that the mass of the soda is 0. So when we do that, we have that the center of mass is equal to h over 2 times the mass of the can over the mass of the can plus the mass of the soda, which is 0. And so this will be equal to h over 2, and so it's still 6 centimeters. Okay, now in part C, we're asked what happens to the center of mass, which is h. So this is h, this is h, as the soda drains out. So let's refer to this variable mass of soda as ms dash. So ms is the initial total mass of soda, and ms dash is the amount of soda that's actually in the can. So ms dash is going to be equal to the density of the soda times the volume. And we can work out the density because we're told the initial mass. So the density is equal to the mass divided by the initial volume, and so this will be equal to ms, which we've got a number for, I'm just not going to substitute it in right now, times the initial volume, and that's equal to the height times the cross-sectional area of the can. So now we've got an expression for the density here, and this volume's actually changing, so we've got ms over h a, and the volume in the can is, well, it's got a height x of soda and it's got cross-sectional area A. So these cross-sectional areas cancel out, and we've got the mass of soda, which is actually in the can, is the initial mass of soda times the height of the soda over the total height of the can. Okay, so our expression for the center of mass is equal to h over 2 times the mass of the can plus x over 2 times the mass of the soda, which is the initial mass of the soda times x on h, over the mass of the can plus the mass of soda in the can, which is given by ms x on h. Okay, so let's times the top and the bottom by 2. We'll actually times it by 2h because that'll make it a little bit prettier. So we end up with h squared times the mass of the can plus x times the mass of the soda, that's x squared times the mass of the soda, over 2h times the mass of the can plus 2ms x. So this expression tells us what happens to the center of mass. You can see that as x drops from h squared to 0, then the numerator decreases, but the denominator also decreases. So it's probably easier to think about it physically. As the soda drains out of the can, the center of mass of the soda goes down, while the center of the mass of the can stays in the same place. So this is going to get the center of mass of the can and soda to drop. But then as this center of mass for the soda is going down, it's becoming relatively less important as the mass of the soda is going to 0. So eventually this mass of soda is 0 and this term doesn't contribute at all. So it's dropping, but it's contributing less and less, which allows it to start coming back up to the center of the can. So when there's no soda left in the can, then the center of mass is back up here. So what happens is the center of mass drops and then comes back up. Okay, now part D is a bit of a challenge. What we'll need to do is look at this expression here, which we've just derived, and what we'll need to do is find out when is this a minimum. So in order to do that, you'll need to work out what dH dx is. So to work that out, you're going to need to use the quotient rule, which tells us that if we call h f of x, then this thing here we can call g of x, this thing here is h of x, then f dash of x is equal to g dash x h x minus g x h dash of x over h x squared. So we can work out what g dash of x is. That's the derivative of this thing with respect to x. So this term has no x dependence, this does. So this is 2x times the mass of the soda, and h dash of x, that's the derivative of this term here with respect to x, so that's equal to 2ms. So what we can do is substitute all these terms into this here to get f dash x, which is this thing. So this is f dash of x. So when we do that and simplify, we end up with 2h times the mass of the can times the mass of the soda x plus mass of the soda squared x squared minus h squared mass of the can mass of the soda all over 2h mass of the can plus mass of the soda x squared. And so to find the minimum, this f dash x has to be equal to 0. So we set this equal to 0, which means that just this bit up the top needs to be equal to 0. So we can solve for when this equals to 0. Once again, there's a fair amount of algebra. So we've actually got a quadratic equation here where this is x squared and then an x term and then a no x term. So with our quadratic equation, this thing here is our a, the thing in front of the x squared. This thing here is our b, and then this is our c, and our quadratic equation tells us that x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. So we can substitute these terms in here and then simplify it, and we end up with x is equal to the mass of the can times the height of the can over the mass of the soda times minus 1 plus the square root of 1 minus mass of the soda over the mass of the can. And we can take the positive square root as x is the height of the soda above the bottom of the can, and that can't be below the bottom of the can, so it must be a positive number. So take positive square root. So now we have x, and then once we have x, the question actually asks us to find the center of mass, so h. So what we need to do then is substitute our expression for x, which we have calculated here, back into this expression here for h. And when we do that and simplify, we end up with h is equal to h times the mass of the can over the mass of the soda times the square root of 1 plus the mass of the soda over the mass of the can minus 1. And then we've got numbers for all these things, so we can substitute in. So we've got 12 centimeters is the height of the can. The mass of the can is 0.14. The mass of the soda initially was 0.354, and then times the square root of 1 plus 0.354 over 0.14, and then we've got our minus 1. Sorry, I left off the brackets around that. And then putting all that into the calculator, we end up with 4.2 centimeters. So if you got that one, congratulations. That was really very challenging with quite a few mathematical steps, but hopefully the physical reasoning about what happens makes sense.